This video is the first of a series of videos that describe two instructional sequences for early number. These sequences were initially developed in classroom-based research projects, and they've been revised and refined as they've been used in numerous classrooms. The sequences are patterning and partitioning, and one that we call structuring numbers. They're designed to foster development of a comprehensive and flexible conceptual understanding of numbers to 20, with patterning and partitioning specifically designed to develop that understanding and foundation for numbers to 10, and structuring numbers specifically designed to develop the conceptual foundation and understanding for numbers to 20, with an emphasis on the teen numbers. In this sense, these sequences form the foundation for a well-developed number sense. The series of videos is organized in the following way. After this initial introductory video, the video segments are divided according to various instructional activities. The next three videos, finger patterns, dot patterns, and the single 10 frame, make up the patterning cluster. These are followed by a single video that describes three activities designed to promote partitioning. And next, there's a video that describes 4 additional activities for small numbers. The videos that describe structuring numbers will follow these. Our intention is to keep each video segment to approximately half an hour. They can be viewed in isolation from one another. However, they will be most meaningful if they're viewed in sequence, because some are going to refer to material from earlier videos. They can be used by individual teachers or in a group setting. If they're used in a group setting, we'd certainly encourage teachers to pause the videos from time to time to discuss questions and issues as they arise. Both sequences were originally designed for grade 1. They're intended for the first half of the first grade year, but aspects of each of these sequences are appropriate for grades K and 2 when adapted appropriately. The various videos will include timelines that indicate when each activity can be used productively. These sequences follow an inquiry approach to instruction. In contrast to common approaches to math instruction, where teachers provide explanations and rules and procedures that students are expected to follow, in the inquiry approach that we advocate, teachers pose problems and tasks that students are expected to solve in ways that make sense to them. The norms that characterize our approach are these. Students are expected to, first of all, solve problems in ways that make sense to them. Everybody is expected to solve a problem in a personally meaningful way. Students are also expected to explain their thinking and reasoning to others. So discussion is an integral part of the instructional approach. Students don't simply report their answers to be assessed by the teacher or by their classmates. Rather, they're expected to explain their thinking and reasoning. And by explaining, we mean that students are expected to clarify their thinking for others so that the others can make sense of them. Students are also expected to listen and attempt to make sense of others' thinking. Now, the phrase attempt to make sense of is deliberate, and it signals that children at differing levels of conceptual understanding might not necessarily have the basis for understanding what everyone else says, but they should at least try to do so. For class discussions to function effectively, it is important that students indicate their agreement or disagreement with what others do and say, and that they feel free to ask questions and offer comments. Finally, students are expected to persist on personally challenging problems and to value such persistence over completing a large number of tasks. Let's think a little more about why we might want to use these instructional sequences, the one we call patterning and partitioning, and the one we call structuring numbers. We've already said that they provide the foundation for number sense for numbers to 20. I want to elaborate on that a little bit. So to do that, let's consider the following. How might young children figure out 8 plus 7 if they don't already know the answer? When we've asked teachers this question, the most common answer they give is children will count on. 9, 10, 11, 12, 13, 14, 15. Well, how does the child know when to stop counting? Why does the child know to stop when he has said 15 if he doesn't already know that that's the answer? Children have a variety of ways to know when to stop counting. Many put up fingers one at a time as they count on and stop when they have 7 fingers up. 9, 10, 11, 12, 13, 14, 15. I have 7 fingers up, so I'm going to stop. Another answer that teachers often give is that the child might say, well, I know that 7 and 7 equals 14, so 8 and 7 has to be 15. Or, I know that 8 and 8 equals 16, so 8 and 7 has to be 15. These two solutions are called thinking strategy solutions. Now, the term thinking strategy is a technical term. It doesn't just mean that the child was thinking. We call a solution a thinking strategy solution when the child uses something he already knows or has just figured out to solve the task at hand. These thinking strategy solutions are clearly more efficient than counting solutions. Well, what if a child reasons like this? I know that 8 is made up of 5 and 3, and 7 is made up of 5 and 2. I can put the two 5s together to get 10, and then there's a 3 and a 2 left. Those together make 5, so I can put the 10 and the 5 together to get 15. Or maybe like this. I know that 7 is made up of 2 and 5, so I can put the 2 with the 8 to get a 10. And 10 plus 5 that's left from the 7 is 15. Or maybe like this. I'm going to take the 3 from the 8 and put it with the 7 to get 10 and add on the remaining 5 from the 8 to get 15. These solutions are really efficient also, and they really reveal a considerable flexibility in working with numbers. These solutions are what we call grouping solutions. So what do we mean by a grouping solution? The child partitions the number into groups, and then he combines them in efficient ways. So you look at the solutions that we have just shown you in the previous slide, doubles, 5s, and 10s played important roles. Teachers invariably agree that they would be delighted if their students could reason in these efficient ways. So the question is, how do children develop these strategies? Well, to answer that question, first we're going to answer a different question. And that is, we're going to say, what is it that children have to know and be able to do to use those strategies? In each of the examples we've given, the child partitioned or split up one or both numbers into parts. In each case, the child then recombined numbers to get a 10. Well, that meant that he had to know the combinations that make 10. Further, in each example, the child went on to add 10 and a small number to get a teen number. Imagine that a child does not yet know that 10 and the small number gives the teen number. Then getting a 10 is of no advantage. Why not get a 9 or an 8 or some other number? The only reason getting a 10 is an advantage is if the child just knows that adding a small number to 10 gives the related teen number. In addition, the child has to be able to use all of this knowledge flexibly. What do I mean? One example we showed was a solution to 8 plus 7 where the child partitioned the 7 into 2 and 5, added the 2 to the 8 to get 10, and then the 10 and the remaining 5 to get 15. So why did he partition 7 into 2 and 5 and not into 3 and 4 or 1 and 6? To us, that's obvious. He wanted to use the 8 to get a 10, and he needed 2 more to do so. But what if the task had been 6 plus 7? This time, to use a similar approach, the child needs a 4 to combine with the 6 to get 10. So this time, partitioning 7 into 2 and 5 isn't helpful. Instead, partitioning 7 into 4 and 3 is useful. In other words, in addition to knowing how to partition numbers, which combinations make 10, and how adding to 10 yields the teen number, the child has to be able to bring to bear all the aspects of this knowledge that are relevant for the particular task at hand. Another way to say it is that the child has to develop a comprehensive understanding of the world of numbers as a whole. In this case, we're talking about numbers to 20. This leads us back to our question, how do children develop these strategies? Or in other words, what does math instruction look like if our goal is that children develop these ways of thinking and reasoning? Our answer to this question is to base instruction on patterning and partitioning, followed by structuring numbers around doubles, 5s, and 10s. Patterning and partitioning focuses on numbers to 10, and structuring numbers focuses on numbers to 20, specifically the teen numbers. These two sequences form the first part of the first grade year. They can also be used productively in the adjacent grades. Kindergarten teachers make use of the patterning and partitioning sequence, but they extend it over a longer period of time. And second grade teachers often find it useful to work with the structuring numbers sequence in a curtailed fashion during the early weeks of the second grade year. As we've already mentioned in subsequent videos, we will describe in detail the instructional activities that comprise these two sequences.